Vapor pressure and change of state. So this will be about vapor pressure. So when we talk about vapor pressure, right, we're talking about vapor. So we have a liquid like water or whatever liquid, gasoline maybe, but water. Let's talk water. You have water, and you have some of that water is going to evaporate. All right, and so two things. Let's clear up evaporation versus vaporization. All right, so evaporation occurs at the surface. All right, so it occurs at the surface of the liquid, and it's very important. It's not at the boiling point. Right, so this is where molecules or particles of the liquid go from a liquid to a gas, but we're not at the boiling point. Whereas vaporization is any phase transition from liquid to gas. Right, so this includes boiling and evaporation. All right, and so like if we're sweating outside doing work or working out or whatnot, we don't want our sweat to boil. We want our sweat to evaporate to help cool us down, right? So anyway, evaporation, vaporization, those are the two words. We'll use vaporization a lot. Okay, so if you have a sample of a liquid, let's look at this. Let's draw a little picture first. All right, I have a container here. Let's say I have let's make it closed. Let's make it a closed container. Let's try that again. So we have a little container here, and let's say we have liquid in this container. This blue liquid. All right, so that would be, let's call it water, whatever it happens to be. So that's my liquid in the container. It's a closed container. All right, and in this closed container, that means it's sealed, so that we have no air coming in or out, whatnot. And we have all these particles of the liquid in here. These are all particles of the liquid, whether water molecules, H2Os, or whatever other liquid you would have. All right. Well, what happens is, right, whether this liquid is open to air or not. So if it's closed, we know we have a water bottle closed. The water's gonna stay in there. Okay. If it's open to air, so let's say that it was open to air, we would know that some of these water molecules would evaporate at the surface. Okay. All right. So if we talk about in a sample of a liquid, right? Okay, whether it's open to air or not, there is a distribution of molecular speeds and kinetic energies. All right, and these are due to thermal energy. Right, now this is just like gases. All right, so some molecules or particles or whatever, some species, it could be an atom, it could be a molecule. So some molecules, move fast or faster, right, with high kinetic energy, high or large, KE, and some more slowly with lower kinetic energy. All right? If the temperature is raised, okay, now temperature is what again? Temperature is the average thermal energy, the average kinetic energy of the sample, right? So that means the average kinetic energy, all right, or thermal energy right, is increased right, and a greater fraction of molecules have enough energy to escape the liquid phase. And when we escape the liquid phase, we're doing this at the surface. What is this molecule right here, this particle? What does it have to? Why does it need energy to escape? What's it escaping from? Well, that means to overcome the intermolecular forces holding the liquid together. All right, that's what that means. Okay, so if I draw an XY graph here, no, undo, didn't work. Try it one more time. So we're going to draw, yes, perfect. All right. And so my fraction of molecules are on the y-axis, right? And the x-axis, I'm going to have kinetic energy. All right? So the fraction of molecules, kinetic energy. And we're just going to draw a little line here. Make that hopefully vertical. So this would be the minimum energy to escape. Right, that's it. So that's the energy we need. Okay, right there. So that's it. So if I get past that, now yellow line, I have enough energy to escape the intermolecular forces. So the cold curve, low temperature, is going to look something like this. With only this fraction of molecules able to escape, right? So this is low T. If I heat this sample, right? If I heat the sample, the area under the curve stays the same, but the fraction that can escape is larger. All right? If that makes sense. So this is higher temperature. Okay? So it's just like we kind of knew this before we even come to class or attend class or watch this video. You knew that warmer water will evaporate or quote unquote dry faster than colder water. We kind of knew that, right? So if we have more temperature, it's more likely for the water to go to the liquid to gas phase. We knew that. All right, here's why. All right, so if we look at this picture again, up here, okay, there are forces. These forces are being pulled, right, in, right? Why are they? So the molecules are pulled in from the surface by your intermolecular forces. Right? In this case, it's surface. That's what surface tension is. Surface tension, that's right. It's the molecules going to itself. Water is attracted to itself. All right. That's why it beads up. Okay. All right. And so when a particle has enough kinetic energy to escape that force of attraction, it can leave and become vapor. Right? So this is liquid and this is vapor or gas. Right? So now the heat required to vaporize 1 mole of a liquid is called the molar heat of vaporization. Right? It's always positive or endothermic. Right? Always positive. Right? And it's delta HV. Right? For example, water, liquid, going to water, gas. Delta HV is positive 40.7 kilojoules per mole. All right. All right. So now we know if we have an open water bottle, glass of water, that it'll eventually dry. Right. Now it doesn't happen fast. If we heat it up, right, if it's hotter water, it'll go faster. Right. Now, I drew a closed container up here. All right. So once these particles become gas, right? So some gas water up there. Some of the gas ones will actually go back down. They will lose energy and go back to the water. Whether they bounce, right? Because they're not static. They're not just floating. They're moving around, right? If you remember gases, they're moving quite fast and bouncing all over the place, bouncing with the container and other gas molecules, and it's going to be the surface of the water too. And if they lose some of their thermal energy, they will go back into the water. All right. So let's write this down. In a closed container, right, when the rate of evaporation, right, so when the rate of when water molecules are leaving the liquid going to the gas, right, equals the rate of condensation. So that's when the gas molecules, like the gas water, is now going to the liquid water, right? So when they're going at the same rate, if I have 5 molecules a minute going from liquid to a gas, and I also have 5 molecules a minute going from a gas to liquid, right? Whatever the rate happens to be, okay? Right, and this works for any liquid, not water, but I'm using water as an example, right? Then the system is in equilibrium. All right. So That's what we have here. When the rates of going from a liquid to a gas equal gas to a liquid, we're in what we call equilibrium. Now, let's recap. If we go back to an open container, this doesn't happen, right? Okay? Because they're so big, then the atmosphere becomes your container, and this doesn't work. It has to be a closed container. All right. At equilibrium, the partial pressure of vapor in the gas phase is called the equilibrium vapor pressure at that temperature. All right, let's talk about that line. So the partial pressure of vapor. So if we're talking about, let's say you have a water bottle with a lid on it that you can close. All right. There's also air in there, right? We didn't make it a vacuum. We just have air, and then you close the lid. Okay. Well, the partial pressure of vapor, in this case water, so the partial pressure of water. So there's there's a total pressure of air in your bottle. Part of that pressure is due to the water. So the vapor would be of the liquid that's we're talking about, in this case water. Right? And how much water pressure is how we measure how much. So how much water is in the gas phase. Right? That's what this means. Right? And it's based on temperature, right? So this is where the vapor pressure is increased, right? The vapor pressure is increased I lost my spot. The vapor pressure is increased as the temperature is increased. All right. The boiling point. The boiling point is reached when the vapor pressure equals the atmospheric pressure. All right, so normal boiling point. Right, is at 1 atmospheric pressure, or 760 millimeters mercury or torr, right? Okay, that's normal. That's what normal is. Okay, so let's recap this. Open container, we know things will evaporate depending on the liquid we're talking about. So you could have, let's say, liquid mercury, very low vapor pressure, not going to evaporate hardly at all. You have water, which will evaporate. You have acetone, nail polish remover, evaporates very fast. It has very high vapor pressure. Okay, it's dependent on the liquid. Now, In a closed container, right? In a closed container, when the rate of evaporation reaches the, or actually, when the rate of condensation reaches the rate of evaporation, when they're the same, right? We call that equilibrium vapor pressure. And it's temperature dependent. So as we increase the temperature, we increase the vapor pressure. So that means as we increase temperature, we increase the number of particles of the liquid that are now in the gas phase. Right? And then when the vapor pressure equals the atmospheric pressure, we boil. So when you're boiling water at home on the stove, right, when the pressure of that water, the vapor pressure equals 1 atmosphere, it starts to boil. And we have anywhere in the liquid now, we're changing from a liquid to a gas. Now, usually that happens at home on the bottom of the pan because that's where your heat source is. But in boiling, it can happen anywhere. Now, if you wanted to, let's say, use a pressure cooker, some people use these, all right, where you seal your container. Now you make it a closed container. Well, as the water evaporates, it increases the atmospheric pressure of that container, right? The atmospheric pressure. And so that's why you can have water boil at a higher temperature than 100 degrees Celsius when you have these like Instapots or pressure cookers, because they are making the atmospheric pressure higher as the water evaporates. All right. So now there is a relationship between vapor pressure and temperature. All right. So now we'll just give it to you as the relationship. So, and one thing is, if we talk about this, we like to make things in this way, where you have x, y, and we like to have some type of line from the origin. It doesn't matter how that line looks. We want some type of line from the origin, right? It doesn't matter if it's a high slope, low, medium, right? Right? We just like to have some type of line. Y equals mx plus b, right? Okay, just to recap. So if I have x here, right? X is right there. And this is the independent. And I have y. Let's use green. Right there. And this is dependent. Right? Y depends on x. We're looking at how y depends on x, right? And m is the slope, rate of change, right? So I can't. Yeah, too many letters there. Let's try slope. All right. Ideally, we want b, the y-intercept, to be 0, but it is what it is. So the slope relates how x and y are related, right? And we love this, okay, because it tells us the relationship to predict behavior. So if we graph the natural log of the vapor pressure, all right, so that's the vapor pressure of any substance, that's going to be equal to negative delta H V over R. OneNote does that to me where it moves on me. Apologize. Times 1 over T plus the natural log of, they just make it B, beta. That's the y-intercept. So you have y equals mx plus b right there. All right. Now we had to take the natural log of everything to make it a straight line, because you'll learn that vapor pressure grows exponentially. All right, exponentially. All right. So now, since at every temperature and vapor pressure have the same y-intercept, I can use what we call the two-point form. Right, where we take this, we have T1 and P1, all right, and P, I would use natural log of P vap 2, all right, equals negative delta H over R, which doesn't change, 1 over T2, right, plus the natural log of beta, right. We know those two are the same. M's the same, and so we can solve these. We can set these equal to each other, right? Because natural log of B equals natural log of B, right? And we can actually make this a two-point form of the equation. And depends on how you derive it, comes up with how you do it. But the two-point form of the equation would be natural log P2 over P1, right? Equals negative. Well, let me use some colors here. P2 on top in this one and P1 on the bottom. Delta HV divided by R, right, times 1 over T2 minus 1 over T1. So I'll use red again. T2, T1. Alright, and one thing I didn't mention yet, R is 8.3145 joules per Kelvin mole. Same gas constant number as 0.08206, but different units. We need the joules per Kelvin mole here. All right. So it's very important that P2 and T2 go together and P1 and T1 go together. That's very important. All right. And so we'll do one example, and then we'll go on from there. So let's do an example of this with propane. Propane has a normal boiling point. So right away, normal boiling point. That means my pressure is 1 atmosphere or 760 millimeters of mercury. Right, and that normal boiling point is negative 42 degrees Celsius. The enthalpy of vaporization is 19.04 kilojoules per mole. The question is, what is the vapor pressure of propane at 25 degrees Celsius? Now I'm going to go back to this. What do you notice here about T in this form? T has to be in Kelvin because it's on the bottom. I can't have 0 down there, right? Okay, all my math colleagues would, heads would explode. We don't want to do that to them. We can't have 0 on the bottom. So, natural log. No, actually, I'm going to do it this way. Natural log P2 over P1 equals negative delta HV over R, 1 over T2 minus 1 over T1. Wonderful. So now, I'm going to have P1 equals, T1 equals, P2 equals, T2 equals, delta HV equals, and R equals. I'm going to just list them. Alright, so R is 8.3145 joules per Kelvin mole. Delta H is 19.04 kilojoules per mole. So if you notice right away, kilojoules and joules, we're going to have to address that. Now most of us have calculators that can handle this without a problem. Alright, and I'll actually open mine, get mine going here so that we can actually have a calculator. You see how I do it. Alright. T2, T1, P2, P1. What are they? So, it doesn't matter which one you pick. I'm going to try to, it says, what is the vapor pressure? So, I'm going to want to solve for that guy. It's always easier to solve for on top than it is on the bottom. Okay? So, P2 is going to be my question. That means T2 has to be 25 degrees Celsius. P1 was 1 atmosphere because it's normal, and negative 42 degrees Celsius. Alright. So, how can I use degrees Celsius? No. Alright, so then what do? I have to add 273, don't we? So I take negative 42 and I add it to 273 and I get 231 Kelvin. And with 25 degrees Celsius, I add 273, I get 298 Kelvin. So those are the temperatures I need to use. Now, there are two ways to go about solving this. You can take e to both sides and then times by P1 and get it, or you can plug all the numbers in and then start solving. I will start by putting all the numbers in because I see a lot of, right, you can do that. A lot of people put all the numbers in, right? So I'd put P2 in there at the question. P1 I'd put in 1 atmosphere, and I'd put in delta H, then R. But you can actually do this. You have a calculator. If you have this type of calculator here, or I have a TI-84 plus CE, but I also have a TI-83, right? Any of these work where you can put all this in one shot. Now, this depends on your calculator skill. All right, if you're confident with your calculator and you know about what our answer should be, like you're good at estimating, I would do it all at one shot. If we're very apprehensive about the calculator and we really should know where we're looking for. So if what ballpark is a good answer? And we'll talk about that in a second. But if you are apprehensive, I would do less keystrokes per enter in your calculator. So if our calculator is still not very confident, I would use less keystrokes per enter, because then you get the syntax error and you can get discouraged and all that. We don't want that. If you're very confident with your calculator, go ahead. All you would do is raise both sides to E. Right? I would do E to both sides and then multiply by P1, and you got it. So P1 times E to all that in your calculator, you're done. It's actually faster. We'll plug in all the numbers, right, and do it the long way for you guys. Okay? All right, and I'll show you on the calculator both ways. So, all right, if I were to do it the way we first did with moving, I'll come to the side. All right, and I would have E to both sides. So natural log of P2 over P1 equals negative delta H V over R, 1 over T2 minus 1 over T1. Raise both sides to E. Right? Same button on the calculator for those of us who aren't very confident with that. And E natural log to E, those go away. Right? And so I would actually end up with P2 over P1 equals E to the negative delta H V over R times 1 over T2 minus 1 over T1. Well, then I just multiply by P2 equals P1 times E to the negative delta H V over R, 1 over T2 minus 1 over T1. And there we go. You just plug in those numbers and you solve. Not bad. If we don't want to do that, we're going to come over here. Natural log. P2 is what I am looking for. P1 is 1 atmosphere equals negative delta H, right? I'm going to do it this way where it's 19.04 kilojoules per mole divided by 8.3145 times 10 to the negative third kilojoules per mole Kelvin. Alright, so that way I'm in the same unit. I could have made the top one times third or the bottom one times 10 to the negative third. Doesn't matter how you do it, you got to do it. You got to do it on this way too, right? It's got to be the same order of magnitude. Alright, 1 over T2 minus 1 over T1. Alright, so T2 is 25 degrees Celsius, or 298 Kelvin. And T1 was 231 Kelvin. Alright, now it's an algebra problem. Okay, and so everything on the right side, I'm going to take the natural log of P2 all over 1 atmosphere. Now, in my calculator, I'm going to do all this. So let's look. How am I going to do this? Negative 1904 divide 8.3145. I use, in this calculator, I have to use this button right here, this EE key. So second, comma, negative 3, right? And I'm going to hit the times just because. Open parentheses, 1 divided by 298 minus 1 divided by 231. That's what I got. Right, 2.2288. Yep, did I do that right? Yes. What was it again? 22288. 22288. All right, units. Well, what units do we have? It looks like kilojoules is gone, mole's gone, Kelvin's gone. There's no units. My units are actually going to be right there, atmospheres. So now I have natural log of that number. So I have to do e to both sides. All right. And so how do I do that? All I have to do is go into, see how natural logs down here, and then I got e to the x. I hit second, e to the x, and I'm just going to write in second answer. And it's going to give me this answer right here. Enter. 9.29. So that means P2 over 1 atmosphere equals 9.29. So multiply both sides by 1 atmosphere. P2 is 9.29 atmospheres. That's a large number, right? 1 atmosphere is normal. So, does that number make sense? Well, if propane normally boils at negative 42, at 25 it should be much, much higher than 1 atmosphere. So that works. Now what about here? What about here? So here I had P2 equals to 1 atmosphere. Well, actually, let me do it this way. Give myself a little bit more room. E to the negative delta HV, which is 19.02. I'm going to just do times 10 to the third joules per mole over R, 8.3145 joules per Kelvin mole, because you can do it either way, times 1 over T2 minus 1 over T1, right? 298 and 231. So how do I do that in the calculator? Well, I have 1. All right, so 1 times, now it's E, right? So I just do second E, open a parentheses, negative 19.04 times 10 to the third, divide, not 9, 8.3145 times 1 divided by 298 minus 1 divided by 231. 2 parentheses, and what do we get? 9.29. Alright, so that's how you do that one. So there's the calculator and everything. Alright, and so that's using the vapor pressure. So what do we calculate here? Vapor pressure, so how much propane is going to be in the gas phase, and it's 9 times the atmospheric pressure, so all of it. Alright, so that's an example of vapor pressure using the Clausius-Clapeyron equation. That's what this equation is, and that's an example of it. All right.